A database is a collection of tables. The tables, in turn, are collections of data organized in rows, where each row represents a unique record within the database. What makes this record unique is the selection of fields or column values within that record that uniquely identify that record within the database. When we talk about keys, there are candidate keys, which can be a single attribute or a collection of attributes that uniquely identify the row. There could be more than one candidate key. We select one of those candidate keys to be the primary key. That is the key that will be used to uniquely identify the row. Now, to be a candidate key, the value or combination of values that are selected must uniquely identify each row in the table, and there cannot be duplicates, because a duplicate would mean that there is not a unique quality to the key among the rows in the table. If we're building a database with tables that have relationships amongst one another, then each relationship between the tables is associated with a primary key from those tables. So the primary key becomes very important in the relational structure of the database. When we have a key that uses a single value to identify the row, we call that a simple key. On the other hand, if we have multiple values from the row that are used in a key to uniquely identify that row, that key is referred to as a composite key. In a relational database, every table should have a primary key defined. Whether that's an artificial primary key where we're generating a value as we insert into the table, or whether that is a primary key that is defined by the natural values of the elements in the table, each table must have a primary key. A primary key does not allow duplicates, and obviously there can only be one primary key per table, and the primary key cannot be absent of value. It must have a value. Careful consideration needs to be made in selecting a primary key. Very large primary keys, that is, primary keys that either use a field that is very large or a composite key that uses multiple fields to uniquely identify the row, the length of the primary key will affect the performance of that table within the system. If our table has multiple candidate keys and some of those were not selected to be the primary key, then we refer to those not selected candidate keys as alternate keys. Again, the primary key is the basis for building the relationships between tables in the database. When we use the primary key from one table to create a relationship with another table, that primary key stored in the other table is referred to as a foreign key. The foreign key is the primary key of the table to which it refers. There's a lot of power available in using foreign keys to implement consistency and referential integrity in the database. So this is a key concept for us to understand. A primary key from one table used in another table to refer to the first table is referred to as a foreign key in the second table. We'll see this in the demonstration, and it should be much clearer at that point. Going back to relationships, if we have two tables that are related in a many-to-many relationship, then the only way to implement that in the database is to have a link table, a table that links those two other tables together based on their primary keys, so that within the link table, the primary keys from each of the tables in the relationship are referred to as foreign keys within the link table. If we have a one-to-one relationship between two tables, then there can only be one occurrence of an element that is related to the first table in the second table, where the primary key of the first table becomes the foreign key in the second table. This is what builds the referential integrity constraint in the database, that there can only be one element in a table that is related to another element in another table, a one-to-one relationship. During our design process, we can define ranges of values that an entity column can contain. These are referred to as constraints within the database. So a constraint can provide a level of business rule implementation, which limits the data that a user can enter into a table. So we can use a unique constraint, for example, to prevent duplicate values in a table. We can have, unlike a primary key, which is a unique constraint, because there can be no duplicate values in a primary key. But unlike a primary key, you can have multiple unique constraints on a table. There are no duplicates, obviously, allowed. This is a constraint that requires that all values for that column be unique. However, null, or the lack of value, is permitted. A very powerful constraint is the default constraint, which permits us, the database designer, to provide a value for a field that will be used should the user or application not provide a value during an insert operation. We can also constrain a column to not be absent a value, to not be null. So the null constraint will reject an insertion if the column on which it is defined does not either have a default value or a value provided by the user or application during the insert operation. And finally, the check constraint limits the range of possible values. Now, it's important to note the check constraint is a very powerful constraint, but the MySQL database system does not enforce the check constraint. The documentation refers to this and says that the check clause is parsed, which means it's understood by the database system, but it's ignored by all of the storage engines. That's straight from the documentation. So understanding the check constraint is important. We can provide a limit on the possible values to be inserted in a field, but it won't be enforced, at least in this version of MySQL Database. We want to avoid spending a lot of time on database theory, because database theory sometimes doesn't translate into pragmatic application in the database design. However, in this case, normalization does translate into good design principles. The whole point of normalization is to reduce the data redundancy within a database design. This has some great benefits for an OLTP system, an online transaction processing system, OLTP, in that it reduces storage requirements by reducing redundant data. And it increases the efficiency of the database. We're going to limit our discussion to the most prominent normalization form, which is third normal form. So we're going to take a database and we're going to go from first normal form. We're going to transition that database design to second normal form and then to third normal form. In all practical applications of an OLTP system, third normal form is generally sufficient for efficient operation of the database system. There are other forms, to be sure. These are very theoretical and we will not be discussing them. So let's go look at some code and see how to design a database and normalize that database.